Good morning, everybody. I hope dinner was good last night, and that's why most people are not here, which is also good because we are going to have some fun. I'm here to present a paper called Samples, Self-Adaptive Mining of Persistent Lexical Snippets for Classifying Mobile Application Traffic. It's a long title, and very fashionable to have long titles these days. But more importantly, sometime around December 2013, I paired up with a ninja, an Indian actor, Dr. Evil, and Chairman Mao, to start a project in which our aim was to find high granular traffic classification in mobile networks. If you haven't seen them before, they actually look like this. So the principal author of this paper, or the first author of this paper, is the student Hongyi Ya. And he can't be here mostly because of visa issues. So I'm here to present it on their behalf. And this work was partially done at Narasin Corporation, which later moved en masse to Symantec Corporation. So that's the background. So what exactly are we peddling here to you? What we want to show, or what we want to achieve as a core networking competency, is the capacity to identify applications responsible for observed network traffic at a vantage point in the network. What do we mean by that? It means that you want to be able to identify exactly what application is responsible for generating the traffic that you observe, either at a Wi-Fi AP or at a network router. And the most important point of this is that you do not have access to the end user's device. You don't have agents running there, and you have no way of knowing what the device is actually doing at the user's end. And we also want to do this preferably at a per flow granularity. The reason being that a network flow is, in fact, an atomic observation at the network level. So in order to put it into a schematic, you can imagine that individual flows are coming in where your analysis engine resides alongside a network element or a network vantage point, like a Wi-Fi AP, or, these are not regular Wi-Fi APs, smart Wi-Fi APs with some amount of processing capacity, or routers. And what you want to achieve is a mapping function which puts each flow and places a label, the application ID, which your analysis engine thinks this flow belongs to. It's easier said than done, as always. But before we get into the nitty-gritty details, the question to ask is, who actually cares about such analysis or such fine-grained analysis, and why? This is mostly important to network operators who want to know what's going on in their network, and also to enterprise network managers. And once you have this sort of fine-grained and detailed view into your network traffic, it facilitates both network measurement tasks, such as usage statistics, application behavior profile creation, and so on, and also network management tasks, bandwidth provisioning, application level firewalls, which is the holy grail of this sort of work, and also some sort of access control. Also, the people who are interested in these kinds of works are some good people in high places who shall remain unnamed. I'm sure some of you have worked with them in the past, and they are your friends too. Typically government agencies who love spying on you. So, what happened? Why is it? What is the fuss about? Application identification in network traffic is not a new problem at all. It's just that the rules of the game have changed. With the advent of the mobile era, you no longer can treat application classification in terms of port and so on and so forth, which we already know. So nowadays, you have multiple platforms. Mostly, the 5 major platforms are Android, BlackBerry, iOS, Nokia Symbian, and Windows Mobile, which have not only millions of applications, but all these millions of applications provide a very, very wide range of functionalities, never seen before in the history of mankind. On top of that, as if things were not very bad already, these days it's very fashionable to allow people to bring their own devices into an enterprise network. This is a nightmare for people who manage enterprise networks, because now you have no control on the devices that are actually functioning within your network, which again validates our assumption initially that you can't assume that you have a presence on the user device or any sort of access to it. Third, the trend is going to continue in future because wearables are here. So what exactly is an application? And who knows what's running on these devices anyways? So the bad news, and the real bad news here, is that most of these applications choose HTTP as their communication protocol. Now, I know some of you might be thinking, oh, no, that's old news. What about HTTPS? Actually, the only difference between HTTP and HTTPS in these situations is the difference that you find between NSF and NSA. That was a joke. Anyways, the good news is that a lot of these applications use HTTP as their communication protocol. Now, if that sounds like a contradiction, it is, but it's a good contradiction to have. Because HTTP is a standard format. And the good thing about HTTP is that you already know that there is a header and there's a payload. More often than not, and more importantly, the payload and header has a lexical structure to it. This can be thought of as a semi-structured text document in which you have well-labeled fields and content that you can analyze lexically. So whereas some people only see black and white, we see 50 shades of gray, and those are identifiers, as you can very well see on the right-hand side of the screen. What you see on the right side is actually a DPI stripped header and the first 1024 kilobytes of an HTTP request, actually a response from a server that goes to a mobile app on Nokia platform. So identifiers, you say. Let's talk to some angry birds. And if you look closely, Donald Trump's hair actually looks like the birds, and the face looks like the hogs. But what identifiers? Behold, if you go to the Android Google Play marketplace, the Angry Birds, the free version of the Angry Birds app has a listing, a market ID listing, which you can see here on the top. It's a string called com.rovio.angrybirds. This is simply a Java package name. So if you develop apps, you know that this is a common convention. This is how you name your apps. And this string is unique. You cannot have two applications listed on the same marketplace which have the same identifier string, which bodes well. But what about other marketplaces? The same app, when it is listed on Apple iTunes, has a 9-digit unique ID with which it can be addressed. On the Nokia OV store, this app has a content ID of 23158. Immediately you see that the Angry Birds app also has its name. The name is also an identifier of sorts, although it need not be unique in certain marketplaces. But why is this important? Oh, by the way, before we go there, in addition to these IDs that you see, in the iOS marketplace, the application package has a metadata file called info.plist, which comes with many more different kinds of identifiers. These are identifiers that a developer defines when he or she is developing the app, and you're free to check this out. This is across the board. The good thing to notice is that these different kinds of identifiers have some lexical context which rhymes or rather is very similar to the actual name of the application. But all of this would be absolutely useless if these same identifiers did not figure in the traffic generated by the app. Lo and behold, it does. This is an HTTP GET request generated by the Angry Birds application running on an Android platform. And immediately you see two things. First of all, the user agent field tells you that this flow was generated on an Android device. If you inspect closely, it also tells you what device it was running on. So if it's Samsung Galaxy S3, you can very well fetch that information as well. Not only that, in some part of the URL, the parameters have a key value pair called msid is equals to com.rovio.angrybirds, which tells you if you could extract this information with high fidelity, you already know that this is the app responsible for generating this flow, which is good news. Makes life simpler. But it's not just that one app. It's not a one-off problem. You see here the HTTP headers of multiple applications which contain in them identifiers of various types in plain text available for everybody to see in different fields of the HTTP header. Some are standard fields, some are non-standard fields. For multiple applications on all platforms. In fact, here you see the headers from the AOL Messenger app on iOS, and you can immediately see that there are certain kinds of identifiers that go in plain text in communications back and forth. Similarly, you have Fox 2 News on iOS. This is a Nokia app called 1001 Essential Words. And here you have Android, which has a field called XRW. This actually is an AJAX field and is only used for rendering purposes. But for some reason, thousands and thousands of apps deem it suitable to send out their own identity as a full field content of this field. From now on, throughout the duration of this talk, we will call any part of the HTTP header that contains an identifier a lexical snippet. So basically, what are we trying to do? We are trying to transform a networking problem of traffic classification into a lexical problem of context generation, right? So anytime you observe a lexical snippet in an HTTP header or payload, we ask three contextual questions. First of all, what kind of identifier is this? So here you see that the tag 1916%20 dogfight, which means 1916 space dogfight, is the application name of an app. Where in the HTTP header or payload does it occur? And we know that it occurs in the transaction payload. This is a response that the server is sending to the device. And in that, this app identifier figures. And finally, what suffix and prefix surround the occurrence of this identifier type? And here you see that ampersand app equals to 1, ampersand mn equals to is the prefix, and suffix is ampersand vs3. So in fact, you can summarize this information into the following regular expression. Extract from TPL whenever you can. Pattern /b marks a word boundary, which means that if you have any special characters or the beginning or the end of a field, anything that follows mn is equal to until the next ampersand, and look up in the dictionary of all the app names that you have for this platform. So if your aim in this world was to only detect this one app in this form, this is the rule that you could write, potentially manually by observing, and then you could do a reverse lookup with the application name to the content ID and report it in your system that this flow, which was observed in the network at a vantage point, belongs to the app ID AF. This is the function 36123, and now you know which app was responsible to generate it. So far, so good. But you can't build an industrial level system by observing one flow or one app or even a few thousands. What you need is 700 to 800,000 applications. That's the kind of scale you want to attain. But that's good news, because this pattern, this observation pattern of getting lexical contexts and summarizing them does not only exist for one particular app. Here, I'm demonstrating how the user agent field of different iOS applications have the same kind of lexical context information, although the regular expressions are different. If you look closely, on this side, three different iOS applications produce user agent fields which have similar lexical structure, not exactly the same, but very similar, in which an identifier of the type CF bundle display name or CF bundle name or CF bundle executable figures at the beginning of the field until the first / followed by a bunch of other stuff. Clearly, we can summarize it into a lexical context of the following kind. Go to the user agent field, look for whatever is at the beginning till the first /, and then that is my extracted string. Now, when I am training this system, I already know what identifier type existed in all the examples that I saw in my training set. Hence, I have to make a reverse lookup with the same kind of thing. This is exactly the kind of thing we saw in the previous example. Here, the extracted string was in fact not the application ID, but a string that we can then reverse map to the application ID. And this information can be generated very easily by simply crawling the application marketplaces. The rule of thumb is, in any kind of analysis of mobile applications, crawling is the cheapest activity, download is the second cheapest activity, execution is the toughest. In fact, it's so costly that it is prohibitive. And then there are legal issues, but we don't bother about that very much. Now, once again, a different kind of lexical context, again for iOS apps. In this case, you observe that there is a key-value pair. For 3 different applications, the identifier type application ID is present in the pair field as a key-value pair. And hence, you can summarize this lexical context as go to the pair field, look for a word boundary. If you see MSID is equals to followed by a 9-digit format, fetch that for me, because I can then go and look up in the list of all the app IDs for iOS, which I have called, and if there is a match, I know it is that particular application. But there is something else here. These texts, like MSID, are very short strings. I mean, I can write an application in which I put MSID equals to something else. So how do you know that the thing that you extracted is actually a valid extraction as opposed to something arbitrary? And that's where conditions come into play. While you train your system, you are also learning under what conditions of other fields is this lexical context true. This is basically reinforcement learning with different sample sizes of the same training data set. It's very standard practice in any kind of lexical rule learning and so on. So essentially, in order to solve this problem at a grand scale, because we had a client waiting in Japan who insisted that we give them not only an infrastructure to identify applications. 3 minutes? Very quick. All right, we shall rush. Our system can self-adaptively learn rules through these lexical contexts with fewer than 2% apps in the training set. It then generates a very low system memory imprint rule engine with fewer than 100 rules in all that can help you identify, or at least in our test sets, more than 13 million flows that are generated by 700,000 mobile applications across 3 platforms. And the false positive rates are lower than 1%. Now, you should take these numbers with a pinch of salt, like any data analytic paper, and if time permits, I'll explain that. And it achieves fairly good put in a controlled environment. The problem with a non-controlled environment or a real-life deployment is that the systems that you have access to in real deployments in these cases are so fast and so strong that good put comparisons with controlled environments is like comparing an apple to Mars. And the key to doing all this is to be able to identify identifiers. In any case, so I'll briefly run over how the system actually works without any supervision. First of all, you have a crawling and download infrastructure in place. The job of this infrastructure is to go to application web pages, get the application executable only for free apps. If you want all the paid apps, give me $1 million and we can do this. Operational result is that you create a repository of web pages and app executables. These are separate. The second step is to do identifier extraction. From the web pages, application web pages that you got, you obviously have the marketplace listing identifier as well as the application name. But there are more identifiers to be extracted from the app executable repos. As I had shown previously, the CF bundle identifiers come in a manifest data file. Similarly for Android, you also have a manifest.xml file which contains all kinds of identifiers in it. Again, all these identifiers do figure in network traffic, otherwise they are useless to us. The most crucial step and the golden child is the app executor. This is one module of our system which taught me to respect engineers, and tremendously so. the amount of effort required to run cross-platform applications in an emulator is so high that this took most of the time, well, other than writing the paper, which was rather boring. And then you do lexical context extraction, as I've shown, using your training sets, and basically you generate a set of rules. This can be done in a reinforcement learning paradigm. I'll be free to take any discussions about this later, or you can read it in the paper. It's pretty self-explanatory, actually. The result is a conjunctive rule. Now, I know that there's something wrong here. Something's been bothering you guys, hasn't it? What about HTTPS? The moment you have HTTPS, all this lexical pattern goes away. Because the only lexical structure you see is the host name, and that's no good at all. Well, HTTPS is a problem. HTTPS is a problem in the wild because HTTPS tramples samples. In the wild, the sample system cannot work if all the traffic it sees all the time is HTTPS. As Sarah Palin says, yeah, betcha. But we know something that you know but haven't seen yet. A woman in the middle. A woman in the middle is a very, very clever and useful way of solving this problem in an enterprise network setup. We already have two demonstrations of these, and these papers have been cited in the paper as well, so you can go and read it. Basically what it does is, if you are a Wi-Fi access provider, you can force all the people who use your Wi-Fi access point to download a certificate, which then makes you the go-between between the end user and the service provider in the internet. Now don't be shocked if I tell you that if you are a cellular subscriber in US, where you buy the devices from your self-service provider, the same thing can be done on your devices as well, without you noticing it at all. It's entirely transparent. What happens after that? Here are two header files, header snippets generated by two things running on HTTPS. This is the Yahoo Messenger. Under the hood, there is absolutely no difference between the lexical structure of HTTP and HTTPS. But most importantly, because of the complacency of the fact that SSL cannot be broken, these people are so careless that they send out your email ID and your passwords in plain text. Which is very good, because someday it will make me rich. And then I don't have to come to any of these conferences and give you talks like these. But essentially, what this shows is, yes, we can. But you will still have reviewers or people who don't particularly pay attention to things, who will ask you, but where's the certificate? This joke works very well in the US. But anyways, doesn't matter. A bit about a summary of the results. We evaluate samples over 651,000 free Android applications, which is huge by any academic standards. These applications altogether produce over 13 million flows. The number of training applications in the case in which we use all the apps was 23,000. And these resulted in 51 beautiful looking rules that provide 96% application coverage. Similar results can be seen for the other two platforms on which we evaluated this. But there is something that I want to mention here, which most academic talks do not have. You should never believe numbers which are above 90%. They are almost certainly false, or at least they're hiding something. When somebody mentions that you have 96% application or flow coverage, what they're essentially telling you is that of those applications which produce at least certain number of flows in which some identifiers lie. If that is not measurement bias, I don't know what is. More importantly, you see that I don't put flow coverage here because it is embarrassingly high. Over 99% of the flows that have any identifiers in them can be identified by the system. But then that's like saying that we are all mammals. It's a tautology. But in any case, these numbers bode well, they were satisfactory to the client, we got the money, life moves on. More importantly, the one question you want to ask is there a sampling bias in terms of what if your sample sizes are smaller? Turns out that not very much. You don't lose much in terms of coverage in good put. Good put definitely goes slightly lower when you have larger rule sets. And that is understandable. Regular expression computations at line speed are extremely expensive. This is not like running Wireshark. We are talking about 20 gigabits per second on Telera cards and so on, and the system has to adapt to that. So that's fine, but you don't see, I mean, the system seems to be very resilient to sampling bias sizes, which is good. Most importantly, there is a leader effect. And what happens is, those rules that have high accuracy and high coverage are very few, but they cover a massive expanse of your application universe. Which is again good, because imagine that you were ready to trade off some amount of coverage for accuracy. And in that case, you could simply pick up these rules, which are high fidelity rules, high coverage rules, and you would be done. So that's nice too. Wait, but hasn't all this been done before? I mean, we aren't the first people or the smartest. Actually, it has been done, partially, in platform-specific scenarios, and with massive assumptions. The first paper to appear, which used some kind of lexical analysis to do identification of apps, a minute, this is almost the last slide, appeared in 2011. And the reason they were doing it was to do behavioral profiling over geographies. So application identification was somewhat a secondary task for them. The way they did it was to look at user agent fields, and they thought that all user agent fields are in fact indicative of unique applications. This turns out to be wrong in 96% applications on Android. 96% of applications on Android never produce a flow in which the user agent is indicative of the application. I would think that's a massive error. The second one was more down to earth. These people were manually inspecting Android manifest files, picking up advertisement key value pairs and looking for them in the flows. Works all right, is heavily human intensive. Network profiler. Now this was a drastic solution. Somebody thought that it would be nice to run an Android application exhaustively, to produce every single flow possible, a priori, create a state machine, and then load it up into a network analysis engine, whereby every time a flow comes in, you run it through all these state machines. Now, if you know anything about graph theory, you know that all longest path match is an NP-hard problem. So it's not only infeasible in terms of training the system, it's even worse when it comes to system performance. Finally, this is the paper by Stanislav Nushkovich, and I don't want to criticize it too much. He's my colleague. All of these people are my colleagues, actually. He's my colleague, but he weighs 2 times as much as I, and he's 2 times taller. So one should pick up fights. So the biggest problem that all these preceding studies had was they were ad hoc, they require a lot of manual involvement, or are computationally too complex to be implemented in a real-time scenario. Most importantly, the approach they take to training is application-specific. They say, we have an application, we want to identify it, now let's train the system. In contrast, our system does not do that. We are more interested in looking at patterns that can help identify multiple applications. Anyways, just for the sake of comparison, we compare it with 2 different kinds of services, and obviously we outperform them. Again, this is not a very informative result, but you can't do much better. So finally, and we have our limitations. What are the limitations? This system will not work for non-HTTP traffic, let alone HTTPS. You can't do this for Skype and other kinds of applications which have their own proprietary way of protocol. It requires constant background effort, adversarial behavior can't be supported, and measuring coverage and accuracy in live deployments is a nightmare. You can't do it because you have no ground truth. Well, with that, you can draw your own conclusions. It's a free country. But we believe that samples can and does, because it's deployed at least 3 locations in the world right now, identification of mobile applications in network traffic at a per flow granularity with high coverage and accuracy across multiple platforms, and it maintains a relatively small memory footprint. We would like to hear from you. You can test it out on your own. Just download Wireshark, download an app, and see if the identifiers actually figure in the traffic you generate. If you generate HTTPS, please look for your passwords. Q&A. With that, I conclude. You can take any questions you like.
Thank you, Radim.